Have you ever heard the saying, nothing escapes a black hole? No light, no information, nothing. But what if I told you that a black hole can actually shine? Not from stars falling into it, not from the hot gas swirling around, but from light emerging from where nothing is supposed to exist, a strange kind of radiation, a faint glimmer dimmed beyond darkness itself. Yet if we understand it, we may grasp the final secret of the cosmos. And today, I'll share with you one of the greatest discoveries in modern physics, something even Einstein never imagined. A quantum phenomenon occurring at the edge of a black hole that can make these devourers of light glow and eventually die. This isn't just a story of science. It's a dialogue between time, gravity, and the void. And the answer lies in a kind of light no one has ever truly seen, but it may forever change the way we understand the universe. Black holes. Two words that evoke both wonder and terror. In most of our imaginations, they are colossal monsters lurking in the cosmos, devouring everything around them like an unstoppable vortex. Once you step beyond their edge, the fateful boundary called the event horizon, nothing can return, not even light. But if light can't escape, then how can telescopes see a black hole? How do astronomers detect light coming from a place where, theoretically, nothing should be able to get out? This paradox has puzzled not just space enthusiasts, but the entire scientific community for decades. And to resolve it, we must first let go of a common misconception. The truth is, a black hole isn't a solid object. It has no surface, no core, no shell. It's a region of space-time where gravity is so intense that all paths lead inward with no way back out. You don't touch a black hole like you touch a planet. You simply fall into it. Like slipping down a slope you don't even notice until it's too late. What defines a black hole is just an invisible boundary, the event horizon. Cross that line and everything including light is trapped forever. And yet, in this place of apparent darkness and despair, lies one of the brightest secrets of the universe. If you've ever seen the first photograph of a black hole, the glowing orange-red ring encircling a pitch-black void, then you've already witnessed something strange. How can something that supposedly emits no light be so radiant? The standard answer is this. The light doesn't come from the black hole itself, but from the accretion disca swirling ring of matter made of dust, gas, and even stars pulled inward. Under the black hole's crushing gravity, this material heats up and shines more brightly than millions of suns combined. But that's not the whole story. Some recent observations have revealed faint, weaker radiation that doesn't seem to come from the accretion disk. And that's where our traditional understanding of light, black holes, and even space itself begins to crack. Could it be that the black hole itself, the very thing that doesn't let light escape, is somehow emitting light? It sounds like a cosmic joke, doesn't it? But this is exactly what one man who couldn't walk, who couldn't speak in his own voice dared to imagine. Stephen Hawking. In the early 1970s, while scientists were still dividing the universe into two separate realms, the macro world of relativity and the micro world of quantum physics, asked a question that changed everything. What happens if we combine both worlds right at the edge of darkness? Hawking dove deep into the equations that describe black holes, and what he discovered was something no one had dared to believe. Black holes are not immutable. They can lose mass. They can evaporate. And most stunningly, they can emit radiation. A region from which light cannot escape could somehow glow, not with ordinary light, but with a quantum phenomenon, one that occurs not inside the black hole, but just outside of it. To grasp this, we must examine something called the vacuum, which we usually think of as nothingness. In everyday thinking, a vacuum is empty, spacino matter, no energy, no light. But in quantum physics, the vacuum is a seething sea of invisible energy fluctuations. According to the Heisenberg uncertainty principle, at every point in space, even in a vacuum, there are random, fleeting energy fluctuations. These give rise to virtual particle pair subparticle and its antiparticle that briefly exist before annihilating each other. They're short-lived, but real, confirmed by experiments like the Casimir effect. And this led to Hawking's groundbreaking insight. What happens when a virtual particle pair appears right at the edge of a black hole's event horizon? The answer is stunning. If one particle falls into the black hole, the other can escape and become a real, permanent particle. This is Hawking radiation, and the energy to create that particle doesn't come from nothing. It comes from the black hole's own mass. Every escape particle takes a little energy away, and as Einstein's famous equation tells us, E equals mc² implies losing energy means losing mass. Gradually, piece by piece, the black hole sheds its mass until eventually it evaporates completely. A tiny quantum effect happening at the very edge of space. Yet, it can determine the fate of entities that once devoured stars, planets, even light itself. The universe is far from simple. You might think that Hawking merely proposed a beautiful theory, a fascinating but abstract quantum idea. But no, he calculated it. With mathematics, with quantum laws, and with a mind that pierced the deepest walls of modern physics, Stephen Hawking did what no one had ever done. He proved that black holes have temperature, and that temperature is inversely proportional to their mass. The smaller the black hole, the hotter it gets, the more radiation it emits. The larger the black hole, the colder it becomes, radiation so weak it's nearly undetectable. For the first time in history, a black hole, a symbol of permanence, of inescapability, became a thermodynamic object. It has a temperature. It emits radiation. It loses energy. And ultimately, it isn't eternal. Just imagine what Einstein once considered an unbreakable pillar of the universe could heat up and melt away, piece by piece, because of invisible quantum fluctuations in the vacuum. And Hawking went even further. He used the Schwarzschild radius, the distance from the center of a black hole to its event horizon, to determine the characteristic wavelength of the emitted radiation. From this, he derived the Hawking radiation spectrum, a faint, cold light, like the breath of a forgotten cosmic furnace. This is no longer philosophy. This is physics. The inevitable result of merging two worlds once thought irreconcilable: relativity and quantum mechanics. With this discovery, Hawking didn't just change how we view black holes. He changed how we understand the universe itself. Black holes can die. We once believed black holes were the endpoint, the place of no return, a one-way door where everything is swallowed and forgotten. But if Hawking is right, then not even darkness can live forever. Because black holes lose mass, and as they lose mass, they evaporate. Smaller, hotter, faster evaporation. Eventually, the process accelerates beyond control. And then comes the finale. A final burst of radiation, mainly gamma rays, the dying breath of a cosmic monster. What about supermassive black holes, like the one at the center of the Milky Way? They would take hundreds of billions of years to vanish, nothing to worry about right now. But if primordial black holes exist, tiny ones formed right after the Big Bang, they might evaporate in fractions of a second, leaving behind an explosion so intense we could detect it with our telescopes. And scientists are actively hunting for such signals. A single such burst, if captured, would be the first direct evidence of Hawking radiation, and the first confirmation that black holes can die. Imagine it, a tiny virtual particle born from quantum fluctuations, from nothingness, being the very thing that destroys a being that once consumed stars, planets, and light. A cosmic reversal of fate. Death does not come from without, but from the deepest gravitational heart of darkness itself. But if it's true, why haven't we seen it? The mechanism is clear. The math is solid. The theory is breathtaking. But there's a problem. We've never directly observed Hawking radiation. Why? Because it's too faint. Picture this: standing before the blazing sun and trying to detect the glow of a nearby candle. That is humanity's challenge. Trying to isolate Hawking radiation from a black hole amidst the overwhelming light of the accretion disk in the cosmic background. Still, even without direct detection, scientists have not stopped searching for ways to validate this theory. In 2019, a research team published in Nature using a Bose-Einstein condensatia supercooled state of matter to simulate how virtual particles might split as Hawking's theory describes. And then there's the Casimir effect, confirming that vacuum fluctuations are real. We haven't seen the radiation, but every quantum sign points in one direction. It truly exists. Now the world waits with bated breath for a single moment, a burst of gamma rays, the final whisper of a vanishing black hole. That would be the living proof for a theory that has waited half a century. And why does this matter more than the death of a black hole? You might say, so what? A black hole emits light and dies. It doesn't affect my life. But you're not just looking at the fate of an object. You're standing before the only known crack between two physical realities. On one side, general relativity describing planets, galaxies, the curvature of space-time. On the other, quantum mechanics, a realm of particles, fluctuations, probabilities, and uncertainty. Both are right, both are powerful, but they don't get along until a virtual particle appears at the edge of a black hole. One escapes, one falls in, and physics changes forever. Hawking radiation is the first link that could unify the entire universe, from the tiniest particle to the vastness of space. This is the theory of everything, what Einstein chased to his dying day, but never grasped. Stephen Hawking, who could not take a single step, opened the first door to that dream. And it all began with one question: can a black hole shine? Now imagine a future far, far away, no suns, no stars, no planets, no life, only darkness. The universe cools, galaxies fade, and the black hole sends devourers of light drift silently in eternal stillness. Until one day, even they begin to vanish. Not by collision, not by force, but by the faintest light ever known to physics, Hawking radiation. A large black hole may take 10 NAS-T or even 10 DU's years to evaporate. A span so vast that the 13.8 billion years of our current universe is but a single breath. But in the end, even the most powerful entities cannot outrun their conclusion. The universe becomes empty. No light, no motion, no echo. And in that final moment, Hawking radiation is the last whisper left to say, the universe once was. One day, we might see Hawking radiation with our own eyes. Or we might not. But one thing is certain. Curiosity, the spirit of asking questions, is what will carry us to the stars. If today's journey moved you, if you love stories that are mysterious, scientific, and push against the final limits of the universe, then please like this video, subscribe to the channel, and turn on the notification bell, so you never miss the next voyage into knowledge. Every share you make not only helps this video reach more people, it sends a message to the whole community of explorers. We keep asking questions because the universe hasn't given its final answer. And you? Do you believe that light can escape from the darkest place? Do you believe that a virtual particle can change the fate of the cosmos? Leave your thoughts in the comments below. I read every one. And I truly believe it's people like you, curious, humble, and passionate about truth, who will help me unlock the greatest mysteries of the universe. I'll see you in the next video. And remember, even darkness must listen to the light.